Hey there, sports fans, etc., etc. Let's look at lesson 4, derivatives of reciprocal trigonometric functions. So, start off, we're going to be looking at show the derivative of y is equal to cosecant of x is negative cotangent x cosecant x. Now for this one, we don't even need to bust out the definition of the derivative, because now that we've got our basic primary trigonometric functions down, we can just use those. So first thing we're going to acknowledge is that cosecant of x is just 1 over sine x, basic trig identity. So we can say then that y is actually equal to sine x to the negative 1, right? So now that we've got it like that, taking dy dx is going to be a whole lot simpler. Dy dx then is going to be, we're going to pull down the exponent, negative 1. This becomes sine x to the negative 2. And then, of course, we have to take the derivative of the interior function by chain rule. That gives us cosine of x. Then we just simplify. That means that I can throw that sine x squared to the bottom. So this is going to be negative cosine of x all over sine x all squared. And then I can split that up into negative cosine of x all over sine x times 1 over sine x. I'm just splitting up that sine x squared. Then both of those simplify. Cos x over sine x is cotangent x. So we've got negative cotangent x times 1 over sine x, which is cosecant x. And done, we've proven it. So this is a really important and useful identity. Now, using the exact same process, I'm not going to do all of them, but using the exact same process, we can get that the derivative of secant x is secant x tan x. The derivative of cotangent x is negative cosecant squared x. And the derivative of tan x is secant squared x. A useful little note, if you've noticed, the derivative of anything that starts with a c is always negative. So cotangent and cosecant x both result in a negative. The ones that don't start with c, secant and tan, they are not negative. So that's a useful, handy trick. I mean, I'll give you these identities on a formula sheet, but honestly, a lot of these you're just going to want to have in your back pocket so you don't have to keep checking a formula sheet. All right, let's get started to a problem here. So we're going to try one here. And we're doing y is equal to x cubed tan 2x. So first off, we want to prove that it's equal to x squared times 2x secant squared 2x plus 3 tan 2x. Looking at this, we've got to remember to use product rule. We've got x cubed and we've got tan 2x. Those are our f and our g. Right? So this is going to be a product rule problem. So we're going to go ahead and say that dy dx is going to be, well, we're going to take the derivative of the first, which is 3x squared. Derivative of f is 3x squared. And then we are going to multiply that by the second, or our g, which is tan 2x, plus f x cubed times secant squared of 2x times 2. So remember, the derivative of tan of x is secant squared of x. So the derivative of tan 2x is going to be secant squared 2x, and then we have to take the derivative of the interior to get that times 2 at the end. So all I have to do now is simplify. So this doesn't look the same as what they originally gave me, but I can adjust this a little bit. I can factor out an x squared. So if I factor an x squared out of both terms, then what I'm left with, if I rearrange my terms a little bit, put that secant squared term first, I get 2x secant squared of 2x plus, and if I factor an x squared out of that first term, I just get 3 tan 2x, which is exactly what I was looking for in the beginning. Piece of cake. Delicious, delicious cake. All right, let's try another one. So in this one, I am given 2 cosecant cubed of 3x squared. So this one's not going to be a chain rule problem. Sorry, it's not going to be a product rule problem, but it is going to be a nice chain rule problem. Lots of chains in this one. So we're going to start by I'm just going to rewrite this one as 2 cosecant of 3x squared all cubed, just to make this a little bit easier to work with. Then when I go to take my derivative, I've got 2 out front there, times, well, I bring down the 3, the exponent comes down, cosecant of 3x squared, but now I have to take the derivative of my interior function here. Sorry, all of that is still squared. Now I have to take the derivative of cosecant 3x squared, chain rule, right? So the derivative of cosecant 3x squared is going to be negative cosecant 3x squared cotangent 3x squared. That's just the derivative of cosecant. But I also now have to take the derivative of the interior function of that. Oops, I forgot a 2 there. So the interior function here are these guys. They go together. I don't have to take it twice, right? That's just the interior function. So I have to take that interior derivative function here, and the interior derivative gives me 6x. And yeah, technically I take that interior derivative again. I get dx, which we can ignore. All right, now all that's left to do is simplify. So when I simplify this down, I can combine all of those coefficients to get 36x, negative 36x to be precise, cosecant cubed 3x squared, cotangent 3x squared. And we're done. Beautiful. Okie dokie. Let's try something a little bit harder. Show that if tan y is equal to x squared, then dy dx is equal to 2x times cos squared y. So this one, the first thing we should take note is that this is going to be an implicit derivative. Implicit derivative. So what I need to do is take the derivative of both sides. So this is going to be d dx of tan y is equal to d dx of x squared. Now, tan y, we know the derivative of that. That should be secant squared of y. But because it's a derivative of y, the function is in terms of y, not x, d dx of the y of the interior function is going to be dy dx. We can't forget that. That's really important. Then we take the derivative of x squared with respect to x, and we get 2x. But when we take the interior function x with respect to x, we just get dx, which again, we can ignore because it's just 1. So now what I'm left with is secant squared y times dy dx is 2x, which makes this really nice and easy. I just divide both sides by secant squared y, and I get 2x over secant squared y, which you can, if you'd like, you can think of this as 2x times 1 over secant squared y, which by our trig identities gives us 2x cosine squared of y. And that's just a trig identity there. And there we go. Proven. Done. Okay. Now for the big one. So our last problem is more of an actual problem. We're going to be showing that the only points on the curve y is equal to cosine x over 2 plus sine x from 0 to 2 pi, where tangent lines are horizontal, so tangent lines are horizontal, are 11 pi over 6, comma root 3 over 3, and 7 pi over 6, comma negative root 3 over 3. So the first thing we should note is what it means to be a horizontal tangent. That says horizontal, which is not the same thing and also not a word. Horizontal tangents. Remember, the tangent comes from the derivative. The derivative is the slope of the tangent line, and lines that are horizontal have a slope of 0. So the horizontal tangent means that the derivative, dy dx, is 0. All right, so first, obviously, our job is to find our derivative. So given what we're working with here, dy dx is clearly going to be found using quotient rule. I mean, again, we don't have to use quotient rule. We could make the denominator into the power of -1 and then use product rule and chain rule, but nah, quotient rule is easier in this case. So again, don't forget, this is my f, this is my g. So I'm just working with those two functions. So I'm going to start with the derivative of f. So the derivative of cosine x is negative sine x, multiplied by g, which is just 2 plus sine x, minus the derivative of the denominator, which is the derivative of 2 is 0, and the derivative of sine x is cosine of x, times just the numerator, our f value, which is cosine of x, all divided by our g squared, our denominator squared, 2 plus sine x squared. But here's the thing. We already know the derivative is going to be equal to 0. That makes things significantly easier. So I'm going to expand out my numerator here. This is going to become -2 sine x minus sine squared x minus cos squared x. That's just me expanding out my terms there. All over 2 plus sine x squared. But I got 0 on the other side. So an easy thing for us to do is multiply both sides by 2 plus sine x. What that does is that cancels this out, 2 plus sine x squared, I should say, cancels that out, and multiplying something by 0 is still 0. And another way to think about it, obviously this is the mathematical approach, but just remember, if a rational expression is equal to 0, then clearly the numerator must be equal to 0, because we know the denominator can't be 0. And really, at the end of the day, it doesn't matter what the denominator is as long as the denominator isn't 0. And the numerator has to be 0 for this to work. So what we get is that 0 is equal to -2 sine x minus sine squared x minus cos squared x. Now this is where you have to get a little bit ingenuity. You got to start looking for those trig identities everywhere you go, right? So if you look really carefully, you might notice something that looks kind of familiar, notably this. This looks a lot like a common trig identity, that sine squared x plus cos squared x equals 1. That's a common trig identity that we like to use. Now, they're not perfect, but if I move those to the other side, then it is. I get exactly what I'm looking for. So I get sine squared x plus cos squared x on this side is equal to -2 sine of x. That simplifies to 1, because we know sine squared x plus cos squared x is 1, is equal to -2 sine x. Then if I just divide both sides by -2, I ultimately get that sine of x is equal to -1/2. Now, using our unit circle, which you should make sure you always have in front of you when you're working on problems like these, whether you have a copy or you make it yourself or you have it memorized. But remember, by our cast rule, we know that sine is only negative here and here, so we know which quadrants we should be looking in. And you just look for the value where sine of x is -1/2. And when you look for those, you will find that the appropriate x values that result are 7 pi over 6, comma 11 pi over 6. Those two are the ones that work for this, that satisfy this equation. Now, notice we've already found the right x coordinates from our original problem. So the only thing we have to check now is that the y coordinates work out. We have to check those. We can't just assume that they're going to work out. Sure, our x coordinates did, but we have to check our y. So that's all that's left to do, is to find the appropriate y coordinates. So when x equals 7 pi over 6, and when x equals 11 pi over 6. Remember, when we're looking for our y coordinate, we don't plug it back into the derivative. We plug it back into the original equation, because we're looking for the points on the original function, not the points on the derivative graph. The derivative is just helping us find the tangent slopes, right? That's about the slopes, not about the actual graph. So we want to go back to the original equation, where we'll get that y is equal to cosine of 7 pi, that's just pi, that's not a 7. I lied to you. 7 pi over 6 all over, let's zoom in here, all over 2 plus sine of 7 pi over 6. So that's just me plugging in our x value into the original equation. And that's negative root 3 over 2. Again, I'm getting these from the unit circle. And 2 minus 1/2. So it's just cos of 7 pi over 6 is negative root 3 over 2. And sine of 7 pi over 6 is 1/2. And when you simplify this, you get negative root 3 over 3, which gives us the point 7 pi over 6, negative root 3 over 3. So far so good. That's one of our points. Let's do the other one. So when x is 11 pi over 6, we get that y is equal to cosine of 11 pi over 6 all over 2 plus sine of 11 pi over 6. And we get root 3 over 2, again just using our unit circle, and 2 minus 1/2. So y is equal to root 3 over 3. Same as the other one, but positive. And that gives us the point 11 pi over 6, root 3 over 3, which is exactly what we set out to prove. All done. All right, and that's reciprocal trig functions. All finished. Good work, everybody. I assume. Homework's at the bottom. Check in with me if you have any questions. Peace.